When we look into the night sky, we are not seeing the whole universe. We are seeing only the portion that has had enough time to send its light to us, a finite sphere carved out by the speed of light and the age of everything that exists. Cosmologists call this the observable universe, and it is not a physical cage or a cosmic wall. Instead, it is a boundary written into the fabric of time itself. Because the universe is 13.8 billion years old, no signal can have traveled farther than the distance light could cover in those 13.8 billion years. And yet, because space has expanded while that light was on its way, the true radius of our observable bubble stretches to an astonishing 46 billion light-years in every direction. Everything inside this sphere is visible to us. Everything beyond it remains forever hidden, its light still traveling, still trying to catch up, still unable to bridge the widening gap. We live, quite literally, inside a bubble of ancient light, a softly glowing shell created not by matter, but by time. Beyond it, the universe continues, perhaps endlessly, perhaps with a shape we cannot imagine, perhaps with regions where galaxies, physics, or even the structure of space itself unfolds in ways we have never seen. In this video, we will travel to the outermost limit of what humanity can observe, the cosmic horizon. We will explore why this boundary exists, how the expansion of the universe shapes it, what lies beyond it, and why this invisible edge may be the most profound frontier in all of science. The boundary of the observable universe exists for a simple but profound reason. Light has a finite speed, and the universe has a finite age. For roughly 13.8 billion years, photons have been racing toward us from every direction, carrying with them the story of cosmic history. But they could only travel so far. There is a maximum distance any signal could reach within that time, and that distance defines the edge of what we can see. At first glance, one might think this boundary should sit 13.8 billion light-years away. But the cosmos refuses to be that simple. While the light was traveling, space itself continued to stretch and swell. Galaxies drifted apart, not because they were moving through space, but because the space between them grew. This expansion means that regions which emitted the light we now observe have been carried much farther away in the meantime. This leads to a deeper idea in cosmology, commoving distance, the true separation between us and those distant regions right now. And when we calculate it, we find that the edge of the observable universe lies not 13.8, but approximately 46.5 billion light-years away. A horizon shaped not only by time, but by the dynamic fabric of space-time. What we see at this boundary is not far away in the usual sense. It is ancient. Every glance outward is a glance backward, into younger versions of galaxies, stars, and even the cosmos itself. The edge of visibility is not a wall around the universe. It is the limit of memory, the furthest moment whose light has finally reached our eyes. The universe has a boundary, not a physical wall, but a limit to what information can ever reach us. Cosmologists divide this frontier into two distinct horizons, each revealing a different aspect of our cosmic isolation. The first is the particle horizon, the outermost shell of light that has managed to arrive since the Big Bang. It marks the edge of everything we have ever seen, from the faint afterglow of the cosmic microwave background to the most distant galaxies captured by modern telescopes. Beyond this horizon lies a vast expanse that has existed for billions of years, but whose light has simply not had enough time to reach us. This is the limit of all signals we have received. The second boundary is even more mysterious, the cosmic event horizon. It is the line that separates regions we can see today from regions whose light will never reach us, not even in the infinite future. Because the fabric of space is expanding faster than light can traverse it, some galaxies are being carried away so rapidly that their photons will forever fall short of reaching Earth. These regions are not merely hidden, they are fundamentally inaccessible. Their future and ours are permanently disconnected. What lies beyond these horizons is not empty. Entire galaxies, galaxy clusters, and perhaps structures we cannot yet imagine continue to exist and evolve. They are real, vibrant parts of the cosmos, but forever sealed off from our perception by the accelerating expansion of space. And this boundary is not static. As time passes, the particle horizon expands, we see more of the past. But the event horizon contracts, we will see less of the future. With every billion years, more galaxies slip beyond reach, vanishing from the observable universe not by fading away, but by being stretched beyond the limits of causality. The cosmic horizon is the universe's silent reminder. Not everything that exists is something we can ever witness. The universe is not expanding into anything. It is the fabric of space itself that stretches, carrying galaxies with it like seeds embedded in an inflating cosmic field. This expansion is not an explosion from a central point. It happens everywhere at once. Every region of space grows, and with it the distance between galaxy clusters increases, even though the galaxies themselves barely move relative to their local neighborhoods. This stretching leads to a counterintuitive truth. The farther an object is from us, the faster it appears to recede. Not because it is traveling through space at extreme speeds, but because the space between us and it is expanding. At great enough distances, this recession speed surpasses the speed of light, a fact that may seem impossible, but it does not violate relativity. Nothing is outrunning light within space. Instead, the space itself is increasing in scale. The engine behind this accelerating expansion is what we call dark energy, a mysterious pressure woven into the structure of space-time. Unlike matter or radiation, dark energy does not dilute as the universe expands. It remains constant, and its influence grows over time, pushing galaxies apart with ever-increasing strength. This acceleration has a profound consequence. Some regions of the cosmos are receding so quickly that their light will never reach us. They drift beyond the cosmic event horizon, not because they disappear, but because the expansion of space outpaces even the fastest possible signal. These distant galaxies evolve in isolation, destined to become forever inaccessible chapters of the universe's story. In this way, cosmic expansion is both a creative and a dividing force. It builds the grand architecture of the cosmos while carving out boundaries of separation, ensuring that much of the universe will remain eternally beyond our sight. When we look as far into the universe as physics allows, we encounter not a wall, but a faint and ancient glow, the cosmic microwave background, the oldest light we can ever observe. It comes from a time when the universe was only 380,000 years old, a newborn cosmos cooling enough for atoms to form. Before that moment, light could not travel freely. Photons scattered endlessly off charged particles, creating a hot, opaque fog. When the first neutral atoms formed, the fog lifted. Light finally decoupled from matter, and the universe became transparent. That first free light has been traveling for more than 13 billion years, stretched into microwave wavelengths by the expansion of space. This is the CMB, the universe's earliest photograph, a glowing surface surrounding us in every direction. But it is not a smooth image. It carries tiny temperature variations, anisotropies, that reveal the seeds of all cosmic structure. Each subtle fluctuation marks a place where matter was slightly denser or thinner. Over billions of years, those differences grew into galaxies, clusters, and the vast cosmic web. The CMB also encodes fingerprints of the inflationary era, a brief moment when the universe expanded faster than any physical process we know. Its pattern tells us how quantum fluctuations were stretched across cosmic scales, shaping everything that exists. And yet, the CMB is not truly the edge of the universe, it is simply the farthest light that can reach us. Beyond that surface lies a deeper, unobservable past, still hidden behind the fog of the early cosmos. The CMB is the last visible echo of a time before structure, before stars, before galaxies, the quiet radiation of a universe just beginning to awaken. Before the cosmic microwave background formed its ancient veil of light, the universe was a very different place, hot, opaque, and turbulent. It was filled with a dense plasma of electrons, protons, and photons so tightly coupled that no light could travel freely. Photons bounced endlessly between charged particles, turning the young cosmos into a glowing ocean of energy where nothing we recognize today, no atoms, no stars, no galaxies, could yet exist. And yet, even in this blinding fog, the blueprint of the entire universe was already written. During the earliest fractions of a second, the universe underwent cosmic inflation, a sudden expansion that stretched quantum fluctuations, tiny variations in density, across enormous scales. These minute ripples in the fabric of space-time became the first seeds, regions where matter would later gather under gravity. We cannot see this embryonic era directly. No light from that time can ever reach us because the universe was still opaque. But we can reconstruct it. The subtle temperature variations in the CMB, just a few parts in 100,000, are fossil records of those inflationary fluctuations. By analyzing their pattern, cosmologists can map the primordial density field, revealing where future galaxies, clusters, and cosmic voids would eventually form. This is perhaps the greatest paradox of cosmology. The structures we see billions of years later, spiral galaxies, massive clusters, vast cosmic filaments, all trace their origins to imperceptibly small ripples laid down before the universe was even transparent. The early cosmos was chaotic, but its chaos had structure. The map of everything that would ever exist was already encoded in the plasma long before light could reveal it. The pre-CMB universe is hidden from our eyes, but not from our equations. Through physics and observation, we can reconstruct a time when the cosmos was only whispers of density, quantum noise stretched across infinity, the quiet foundations of a universe waiting to be born. When we ask whether the universe is infinite, we're really asking about two things at once: its geometry and its topology. Geometry describes the shape of space. Topology describes how that shape is connected, folded, or repeated. And surprisingly, modern cosmology does not give us a simple yes or no. There are three fundamental possibilities for the geometry of the cosmos. 1. An open universe, hyperbolic, saddle-shaped, curving outward. In such a cosmos, parallel lines diverge and space expands endlessly. This geometry naturally suggests an infinite universe. 2. A flat universe, Euclidean, the kind we learn about in school. Here, triangles behave normally, and parallel lines remain parallel. A flat universe can be infinite, but it doesn't have to be. 3. A closed universe, spherical, curving back on itself. Like the surface of a globe, you could travel in one direction and eventually return to your starting point. This geometry implies a finite universe with no edge. So which shape describes our cosmos? Observations from WMAP and later Planck, the most precise cosmology missions we've ever launched, show that the universe is extremely close to flat, so close that its curvature, if any, is smaller than we can currently measure. On cosmic scales, space behaves just like Euclid imagined. But flat does not automatically mean infinite. Space could be flat and still be topologically finite, shaped like a torus, a 3D loop, or an even more exotic multi-connected form. In such a universe, you might look far enough in one direction and eventually see light that originated from behind you, wrapped around cosmic space. We simply don't know yet. The observable universe is limited by the cosmic horizon. Anything beyond it is forever hidden from us. And so the question of infinity, whether space stretches without boundary or folds in elegant, unseen patterns, remains one of the deepest mysteries in all of cosmology. We may live inside an infinite expanse, or inside a cosmic hall of mirrors. Even if the universe is geometrically flat, it may still possess a far stranger property, a finite size without a single boundary. This is where topology enters the story, the study of how space is connected, folded, or wrapped. One of the most intriguing possibilities is a toroidal universe. Not a 2D donut, but a three-dimensional torus, space where every wall connects back to itself. Imagine a cosmic room where walking through one wall brings you back from the opposite side, endlessly. There is no edge, no cliff, no border, only continuous space looping back on itself. In such a universe, large-scale structures, galaxies, clusters, filaments, could theoretically repeat across the sky. If space folds onto itself, light could wrap around the cosmos multiple times, creating echoes of the same object at different positions. A cosmic hall of mirrors, a vast mosaic of repeating patterns. Astronomers have searched for these repetitions in the cosmic microwave background, matching circles, mirrored orientations, identical temperature patches. So far, no such signatures have been found. The universe appears too large, or too subtly shaped, for us to detect any topological wrapping within the observable region. But mathematically, the possibility remains wide open. Our cosmic horizon hides almost everything about the true global shape of space. Beyond it, the universe might twist, loop, or interconnect in ways we cannot yet perceive. A finite cosmos with no boundary is not science fiction. It is a perfectly valid solution to general relativity. We may be living inside a universe that closes on itself, beautifully and silently, far beyond the reach of our light. To understand what lies beyond the observable universe, we must go back to the first fraction of a second after the Big Bang, to the era of cosmic inflation. During this unimaginably brief moment, space itself expanded at an exponential rate, faster than anything we can truly visualize. In less than a heartbeat, regions once smaller than an atom were stretched to cosmic scales. Our observable universe, the entire 46 billion light-year bubble we can see, is only a tiny fragment of that vast inflationary expansion. A single patch on an enormous cosmic tapestry. What we call the edge is not a true boundary. but simply the limit of the light that has had time to reach us. Beyond that limit, inflation predicts far more. Endless stretches of space, far outside our view, expanding too quickly for light ever to cross the gap. These distant regions could contain clusters of galaxies, vast cosmic webs, and structures similar to our own, forever invisible to us, not because they do not exist, but because the expanding fabric of space keeps them eternally out of reach. Even more astonishing, inflation suggests that different regions may not be identical. Tiny quantum fluctuations, magnified by expansion, could create zones with different physical constants, different energy densities, even different laws of physics. In this view, our universe is not the universe, but one bubble among countless others in a grand inflationary multiverse. We will never see these other domains. Light cannot bridge the ever-widening distance. No signal can cross the cosmic divide. But the mathematics of inflation allows, perhaps even requires, them to exist. What lies beyond our horizon is not darkness or emptiness, but a vast and unreachable expanse, a cosmos far larger than the one we can observe, shaped by the same primordial explosion, yet forever hidden from our sight. The universe we know is just a window into something immensely greater. In modern cosmology, the idea of a multiverse is not born from fantasy, but from the mathematics of inflation. According to this theory, the early universe did not expand uniformly. Instead, quantum fluctuations caused different regions of space to inflate at slightly different rates. Some pockets slowed down, creating bubbles like our observable universe, while other regions continued expanding forever. This leads to what physicists call the inflationary multiverse, a vast cosmic landscape where each bubble represents a separate region of space-time with its own vacuum energy and possibly different physical parameters. These bubbles are not parallel worlds in a fictional sense. They are simply parts of the larger inflating space-time, forever separated by distances that grow faster than light can cross. Because of this accelerating expansion, we can never interact with these other regions. Their light cannot reach us, and ours will never reach them. They lie permanently beyond our cosmic horizon, outside the portion of the universe we can observe or influence. Quantum mechanics strengthens this picture. Even tiny fluctuations in the early vacuum state could seed entirely independent realities, each evolving according to its own initial conditions. From a scientific standpoint, this is not speculation for its own sake, but a natural consequence of the same equations that correctly describe the cosmic microwave background and the large-scale structure of our universe. Yet, despite its theoretical strength, the multiverse remains untested. No experiment can currently reach beyond the horizon. No observation has revealed another bubble universe. The theory is taken seriously because it emerges from the most successful models of early universe physics, not because we have seen other universes directly. In the end, the scientific multiverse is not an invitation to fantasy. It is a reminder that the universe we see may be only a small island in a far larger cosmic ocean, one we can describe with mathematics, but never truly visit. When we speak of the edge of the observable universe, we often imagine a boundary, a cosmic wall beyond which nothing exists. But in the CDM model, our best description of reality, this boundary is not physical at all. It is simply the limit imposed by time and the speed of light. Beyond it, the universe continues, unbroken, into realms we will never see. According to the mathematics of cosmology, the regions outside our horizon are not exotic or empty. They almost certainly contain the same kinds of structures we observe here: galaxies, galaxy clusters, cosmic filaments, dark matter halos, drifting gas clouds, and the vast gravitational architecture shaped by billions of years of evolution. The laws of physics do not suddenly change at 46.5 billion light-years. Only our ability to receive information does. In fact, more than 90% of the entire universe lies forever beyond our view. Light from those regions will never reach us, not even in infinite time, because cosmic expansion carries them away faster than light can close the gap. We inhabit a small illuminated island within a much larger cosmic continent. And that unseen continent may be enormous, possibly hundreds or thousands of times larger than what we can detect. It may even be infinite, extending endlessly in all directions. Nothing in CDM forbids such a possibility. The observable universe is simply the path whose light has arrived. Beyond the horizon, space might also have a different curvature. Our measurements indicate near perfect flatness locally, but the global shape could still bend gently across unimaginable scales. Likewise, the topology of the universe, the way space is connected, could differ from our expectations. It might loop back on itself in ways that only become apparent on scales far larger than our visible bubble. All of these possibilities are consistent with current physics. None contradict the cosmic microwave background, galaxy surveys, or general relativity. The truth is simple and humbling. The universe does not end where our vision ends. It continues, following the same laws, filled with stars and galaxies we will never know, a vast realm whose existence we can describe but not observe, a silent extension of the cosmic story unfolding beyond our reach. The cosmic horizon exists not because the universe has an edge, but because our past does. Everything we observe is limited by the age of the cosmos and the time it takes for light to arrive. The horizon is simply the furthest moment in history whose light has had enough time to reach us. It is a temporal boundary, not a geographical one. As the universe grows older, this boundary slowly expands. With every passing year, light from slightly more distant regions finally arrives, revealing a bit more of the cosmic tapestry. In a very literal sense, patience allows us to see farther into space. But this outward growth has a limit. While some regions drift into view, others are carried away by the accelerating expansion of space. Their recession speed exceeds that of light, not because they move through space too quickly, but because space itself stretches between us faster than light can cross. These regions will forever remain hidden. Their light will never reach us, not even in infinite time. Thus the horizon is a delicate balance between what approaches and what flees, a moving shell around us defined by physics, time, and the restless expansion of the universe. We see a boundary not because the universe ends there, but because our ability to receive its story does. The edge of the visible universe is not a barrier, it is a mirror made of time. When we look outward, we are not gazing into distance but into memory, into an era when light was young and the cosmos had barely learned the laws that would shape its future. Every photon that reaches us is an echo of a moment when the universe did not yet know what it would become. And beyond that horizon, in regions forever hidden from our eyes, space continues its silent work. It forms galaxies that will never shine for us, stars whose light will never touch our world, and structures woven from gravity and darkness that grow without witness. These unseen realms are not imaginary, they are as real as our own, bound by the same physics, unfolding in the same cosmic story. We simply exist too far, too late, to ever know them. The horizon reminds us of our place, a small island of light surrounded by an endless ocean of possibility. It teaches us that the universe is larger than our vision and more mysterious than our understanding, and that some truths lie not in what we can see, but in the humility of knowing that so much will forever remain beyond our reach.